We now want to take a look at something called the definite interval. We want to define it and then try and understand that definition and use that definition to calculate a couple of definite intervals. The definition is lengthy enough to where I don't really want to write it out by hand. I'm going to jump to the textbook, and the definition is here. Definition says that the definite interval is if a function is defined on the closed interval from a to b, we're going to divide that interval into n sub-intervals of equal width. Delta x symbolizes the width of an arbitrary interval, and it is b minus a, which is right end minus left end, divided by n. They then let x values denote the endpoints of each interval. The first left endpoint will be equal to a, the last right endpoint will be equal to b, and these x sub 1 star, x sub 2 star, etc. are sample points from within each interval. Then they define the definite interval of f from a to b as being the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I star times delta x. And what they're basically doing with this multiplication is they're finding the area of each rectangle. They're adding up all those areas, and they're taking a limit as the number of rectangles approaches infinity. It's worthwhile to say that they are defining it, and it was defined using just sample points from within the interval. But numerically speaking, the calculation will come out the same whether you use a right-hand endpoint in the interval, left-hand endpoint of the interval, or just random point from anywhere within the interval. And just as a sheer matter of computational convenience, they make each interval the same width, when in reality, they don't have to be. The intervals can be of different widths. The calculation becomes practically impossible if they are. But mathematically, it is just as sound to say that they are of unequal widths as they are equal widths. Now, this notation that they use, it deserves a little bit more discussion, so let's take a look at that. All right, first of all, the A and the B tell where you're integrating from and where you're integrating to. The f of x is the curve under which you're integrating, and the dx, for the time being, it should suffice to say that the dx just tells you that the variable that's going to be used is going to be the x variable. Now notice the symbol. That's the integration symbol, all right? And it may look like a strange or slightly odd symbol, but it's actually just a stylized and elongated S. S for sum, all right? Because what we're calculating is known as a Riemann integral, and we do it with a Riemann sum. That summation is the brainchild of a German mathematician by the name of Bernard Riemann, who studied under Gauss. And frankly, there is no greater credential than to either be Gauss or have studied under Gauss. And so what this is doing is basically finding the sum of infinitely many rectangles under the curve f of x with the variable being x. That's what the dx is telling us, all right? So, for example, here's one we've seen before. We previously looked at y equals x squared, and we looked for the area under the curve from 0 to 1. We found it to be 1/3. Now, we found this 1/3 using right-handed rectangles. All right, and that's what the definition doesn't tell us to do, but it's the same. It could be done with right-handed rectangles. It could be done with left-handed rectangles. Again, noting that each width is going to be positive. And specifically with this curve, each height is going to be positive because x squared always takes on positive values. The definition, strictly speaking, is saying take one of your intervals. From within that interval, pick any number and define the height of the rectangle using that basically randomly chosen value. It's saying it doesn't have to be the left end, doesn't have to be the right end. It can be just a number from within it. Okay, so how should we interpret the answer? What is the answer to a definite integral? Well, in this particular case, and maybe a better sketch would be, this sketch will do for this. In this particular case, since this particular curve is totally above the x-axis, then again with positive rectangle width and positive rectangle height, this 1/3 should be thought of as the area underneath that curve. That's the way it should be interpreted. All right, so for curves that are strictly above the x-axis, that definite integral gives you area. All right, now on the other hand, if we had a curve that spent part of its time above the x-axis and part of its time below the x-axis, well, these rectangles are going to have positive width, which again, they always will, that'll never change, and positive height. So this will give you a positive number. On the other hand, these rectangles will have positive width, but negative height. Again, when you're below the x-axis, your function values are negative. All right, so if you integrated from A to B for this curve, this f of x dx, what you're going to get is not area, but net area. Meaning, if the positive region is larger, then the positive region, take away the negative region, will give you a positive result. If the negative region was larger, and I've kind of drawn it that way, then the negative, take away the positive, will give a negative result. Either way, you're not getting area, you're getting net area. All right. Now, therefore, what interpretation would go with that? Well, it would depend on what area means. All right. In the particular context. With this particular curve, if x squared was the function that modeled the motion of an object, we all saw previously that area under the curve, when you're graphing like velocity, tells you area in those cases is distance traveled, right? And it would be actual total distance traveled. Whereas in this particular case, if you had some positive velocities and some negative velocities, and negative velocities could just mean going in the other direction, and you're asking for total distance traveled, this wouldn't give it to you. This would only give you a net distance from starting point. All right. So again, if your curve's totally above the axis, that's your area. If it goes above and below, that's a net area. The point being, sort of an underlying point here, is a definite integral will always give you a numerical value. Definite integrals are always numerical. The actual meaning, the actual interpretation of that number could vary, but they are just numerical values. All right, so with that in mind, let's grab a function and let's calculate a definite integral by definition. All right, and what you'll find with this is that doing that by the definition, just like with the derivative, is more difficult than doing it with some shortcuts. And are we going to see some shortcuts? Yeah, there will be some shortcuts. But for now, we're going to go by the definition, and we're going to integrate from 0 to 3. The function that we will integrate is an x cubed minus a 6x, and we will be integrating with respect to x. All right, so how should we interpret our answer? The answer will be numerical, but how should I interpret that number? Well, if we put that function into the calculator and graph it, we see that starting at 0, it's passing through the origin, so it's at 0. Move to the right of 0, move towards 3, and you are below the x-axis, so this interval for parts of it will have negative area. Around about 2.5, you're back at the x-axis, and after that, you're above it. So this function when you're moving from 0 to 3 will be sometimes below the x-axis and sometimes above, which means we will not be calculating area. We will be calculating net area. So putting this into the definition, this is going to be the limit as n approaches infinity of f of, let's just write out the definition, why not? F of x sub I times delta x. Okay, so let's figure these components out. First of all, let's sort of step aside and say, okay, what's delta x going to be? Well, the interval's right hand is 3, its left hand is 0. So 3 over n is going to be my delta x. So let's come down here and start filling in these pieces. This is the limit as n approaches infinity. And the delta x over here is a 3 over n. All right. What is f of x sub I? Well, we will start at 0. If you sort of imagine your little intervals, okay, here's 0, we're going out to 3. We start at 0 and we step over a distance of 3 over n, and then 3 over n again, which would put us at what? 6 over n, and then again and again and again. And we do that until we get, we're counting by increments of 3 over n until we get to the other end. So x sub I is 3 over n I times. You're going to do it that many times. I times, you're going to take these steps that are 3 over n wide, 3 over n, 6 over n, 9 over n, 12 over n, and so on. Okay? All right, so once again, I'm going to take that and put it into the function. That's going to be and I'm just going to put the I on top for, just to compress this, 3i over n to the third minus 6 times 3i over n. That's just plugging it into the function, and there's your delta x. Okay, now we're taking a, and I dropped the limit as summation. Sorry, I just dropped my summation notation. Completely lost it. For I equals 1 to n, summation I equals 1 to n. Just forgot to write it down. Summation for I equals 1 to n. All right, I noticed that summation notation missing because I was about to say that since the summation notation is using an I right here, I equal 1 to n, that means n for the moment can be treated like a constant, right? N can be treated like a constant when it comes to the summation, but not the limit. So I can take the 3 over n and throw it out front of the summation notation. And then I can start cleaning this up. 3 cubed is a 27, and then an I cubed over n cubed minus 6 times 3 is 18 I over n. Okay. All right. So again, the reason I was able to throw the 3 over n out front of the summation, because right here the summation is telling you that I is the one that is behaving like a variable, not the n. Okay, then I'm going to distribute. Leave that out. This is a summation from I equals 1 to n of a 27i cubed over n cubed minus a summation from I equals 1 to n of an 18i over n. Okay, and then doing the same thing again. Limit as n approaches infinity, 3 over n. Okay, and that's times all of this, of course. Once again, I can take the 27 and the n cubed. Oops. N cubed, not 3n. N cubed, throw it out front. And all I have here is a summation from I equals 1 to n of an I cubed. minus here, I can take the 18 and the n and throw them out front. And there I've got an I. All right, again, throwing things out front that behave like constants. All right, now, as far as the summation is concerned, there are formulas provided in the book that you'll need to use. And so that becomes limit as n approaches infinity, 3 over n, 27 over n cubed. And the formula in the book specifically will tell you that the summation from I equals 1 to n of n cubed is an n times an n plus 1 over 2 squared minus the summation from I equals 1 to n of just plain I is an n times an n plus 1 over 2. Okay, so that's the summation part. The summation part is finished. So now I need to do a little bit of cleanup. All right, algebraic cleanup. This is the limit. N approaches infinity of a 3 over n. Okay, what's going to happen here is I'm going to have the 27, the n cubed, 2 squared is a 4. You're going to have an n squared and an n plus 1 squared. I'm basically just going to distribute that square. Minus, here, what would be simplest to do is just let the n's cancel. And 18 over 2 is a 9. So that would be easy right there to handle. And then next, so got that 3 over n sitting out front. What's going to happen here is the n squared will cancel one of those n's. You're going to have a 27 over a 4n. And from there, what I would like to do is go ahead and square out the n plus 1. That would be an n squared plus a 2n plus a 1. Okay, minus, and then I have a 9n and a minus 9. All right. Then from there, what's going to happen is I'm going to go ahead and I'm going to multiply 3n all the way through. Limit n approaches infinity. 27 times 3 is an 81. N squared plus 2n plus 1. All right, over, okay, 4n squared minus, multiplying here, I get a 27 because those n's cancel, minus 27 over n. All right, and it's getting closer, I promise. This is the limit. N approaches infinity. All right, multiplying here, I get an 81 n squared plus 162n plus 81 all over 4n squared minus a 27 minus 27 over n. All right, now, finally, at this point, after all that, I can take the limit as n approaches infinity. All right, we noticed that, we've seen before, we divide through by the highest power of n, which means this part will go to 0, that part will go to 0, those will cancel, and you get an 81 over 4 minus a 27, and that goes to 0. Okay? And 81 over 4 minus 27 is negative 27 over 4. Okay? So all of that, just to get down to a net area of negative 27 over 4. That means the positive portion of that area was a lot larger than the negative side. I'm sorry, the positive side was a lot smaller than the negative. That's why the answer came out negative. All right. So what you're going to find in the text, if you read on, you go back to the book. All right. In the book, you will discover the definition that I've mentioned here already is present for you. All right. And from there, these formulas that I was talking about for the sum of I squared, sum of I cubed is there. The formulas for sigma notation we've already discussed. You can divide summations up across addition. You can divide them up across subtraction. Constants can be moved out front. That's been discussed previously, right? And where that becomes most convenient is with these properties of intervals. You'll find that with an integral, a constant can be moved out front. With an integral, you can distribute across addition and you can distribute across subtraction, and constants can be moved out front of integrals just like they can summations, right? And one last thing to mention, they discuss a midpoint rule. The midpoint rule basically says that when you're doing an integral, you can use not just the left-hand side of the intervals, the right-hand sides of the intervals are randomly chosen points. You can use the midpoint of the intervals. And the reason the midpoint rule is brought up is because for evaluation purposes, midpoints usually give better numbers than left-hand ends and right-hand ends. So if midpoints are obtainable, like they're going to show the midpoint rule using it on the reciprocal function, they're using the midpoints of the intervals instead of left-hand ends and the right-hand ends. And again, what you will find is that gives a better approximation. All right.